pleasure to welcome our speaker today, Rostyslav Kravchenko from Northwestern University, and he's going to tell us something about characteristic random subgroups and their applications. First try.
Thanks. Thanks for inviting me. It's a pleasure to be here. So I'm going to talk about characteristic random subgroups, and so it's kind of a review, but it's also a proof of certain results. So there are going to be some proofs. Okay, it's not like it's completely quantum talk. So I'm going to start about just with definitions and explain why they matter, and then kind of go from there. So everybody knows what is a normal subgroup in a group, and I'm going to start with that. So normal subgroup N, it's a subgroup which is invariant under conjugation. So and G is for all elements in G. Now, if you think about set of all subgroups, let me denote it somehow, sub G. So it's a set of all subgroups of the group G. Then this N, any normal group, it becomes a point in the set which is fixed under conjugation. Okay, and now I'm going to make this definition probabilistic and generalize it. So I'm going to say that invariant random subgroup, IRS, so definition IRS, invariant random subgroup so I'm still going to take this space. I'm going to say that I'm taking any Borel probability measure on it. So is Borel probability measure on this group, on this set of subgroups, which is invariant under conjugation. So that mu is invariant under. Okay, so it's obviously a generalization of a normal subgroup notion. Yeah? If you think about normal subgroup as a measure on the set of all subgroups which gives value weight 1 to this subgroup N, then it's is a particular example of IRS. But you can of course take any consider any other probability measures as long as they're invariant under conjugation. They give you this kind of notion.
What does Borel mean here? What does
Borel
mean here?
Borel measures. Well, I mean there is a topology here. Yeah.
Oh.
So and Borel means with respect to the topology,
I see.
which I don't really want to define.
Well, the closed subsets of a Borel space form like standard Borel space.
I was wondering about which topology.
No, it's not discrete. Yeah, okay. There is topology. It's actually compact. So we're going to.
Topology.
Chabuti topology. You define.
I can say what the Borel sets are.
What's this topology on the subgroups?
Let's say like that. So if I take G is discrete, then yeah, G. So it's set of all subsets. Yeah.
2 to the G.
So it's 2 to the G.
Well, I mean it's a restriction of topology here on this subspace.
So it's the Cartesian product of 2 points.
Yeah.
In particular, this is closed, and therefore, well, it's compact because this is a closed subset. So it's compact. Okay, so that's a notion which was defined explicitly quite recently by Abert, Virag, and Glasner, and they used it to generalize some theorem of Kesten from a normal subgroup to this random invariant random subgroups. I can also say that it comes up naturally from any dynamical system. So if you have a dynamical system of group G, so G acts on some measure preserving on some set X with measure mu, then you take what can how can I get random subgroups there? Oops. So you take X and X and you assign to it the stabilizer in G of X. And in this way, you get, so if you take a random X with law nu, then you get a random subgroup in your group. And it's going to be invariant conjugation because that's how stabilizers behave. Okay? Because it doesn't really give you anything new if your action is essentially free, if there are no non-trivial stabilizers. So it would just go into be a trivial subgroup. But whenever you have a non-essentially free action, and there are a lot of them, you actually get some IRS from that action. So you can say that IRS is a part of any dynamical system which is related to the group itself. So it's kind of natural to, if you want to study dynamical systems, it's kind of natural to study IRSs. There were also, so there are several notions, several directions of study. People use it, for example, Bowen used it in order to find out what the range of Furstenberg entropy is for free groups. So he defined a lot of IRSs on a free group and used it to find out that the range of Furstenberg entropy, the range of values of the Furstenberg entropy is actually some kind of interval. You can also wonder how many IRSs are there in a given group. And one of the first results, which was proved even before this notion was defined explicitly, it was in some kind of 1986, I guess. Zimmer and his student proved that for simple Lie groups and for the lattices, there are no non-trivial IRSs. So they are all kind of, there are countable number of them, and they all just come either from a normal subgroup or a finite extension of the normal subgroup. Sorry, I said, did I say simple Lie groups? Yeah, I meant simple Lie groups of rank bigger than 2. Because when rank is 1, that kind of gives you an example of a free group, and in free group, you have a lot of IRSs. And so I'm going to say something more general. I'm going to prove to try to prove a theorem which tells that a lot of groups of geometric nature contains a large number of non-trivial IRSs, and I would explain what do I mean by geometric nature and what do I mean by non-trivial IRSs. So I have a theorem 1. So if G is either non-elementary hyperbolic group, okay. Parabolic, or maybe in class group, with for negative surfaces of negative Euler characteristics, so or outer automorphism group of a free group. Then G has uncountably many non-atomic ergodic IRSs. Okay. So I'm not really going to define all the terms here because I'm going to use a theorem that tells that I can only actually consider free non-abelian group. But first I need to explain what do I mean by. So non-atomic means that there is no, it's a measure, okay, and it's a measure in a space. Non-atomic means that there is no point in that space which has a weight bigger than 0. So in particular, there are many IRSs besides normal subgroups. Ergodic, well, ergodic, yeah, I'm going to try to do it in a short way. So it's a dynamical system. It's a measure which is invariant under an action of a group. So ergodic means that you cannot decompose it, write it down as a convex combination of two other such measures. Okay. So if you have a general definition of ergodicity, if G acts on X and 0, then mu is mu is G invariant. So it's ergodic if it doesn't contain subsets of non-trivial weight which are G invariant. So mu is ergodic if there is no A in X, so that the weight is strictly between 0 and 1, and A is G invariant. Again, it's kind of natural that you don't want to consider non-ergodic measures because you decompose them, and then if you know that there are a lot of ergodic measures that you can get even more by taking convex combinations, and therefore it's kind of natural to consider only ergodic ones here. Okay, so as I said, I'm not really going to use any of the geometric properties of those groups. I'm just going to state another theorem for free group and then use it here. But before I do that, so I'm going to define some invariant random subgroups in a free group and then transfer it to those groups. It's kind of difficult to transfer invariant random subgroups because conjugation is difficult to transfer from one group to the other group. So I'm going to define another notion and then which is more restrictive, and then use it in my construction. So another definition: characteristic random subgroups random so it's still a random subgroup. So it's still a measure on a set of all subgroups. So is Borel probability measure mu on sub G, which is invariant, So it's going to have more invariance, and if it were just IRS, it would be invariant under conjugation. Now I'm going to say that it's invariant under all automorphisms of the group G, under all elements, all automorphisms of G. In particular, it's invariant under inner automorphisms, which are just conjugations, and so any characteristic random subgroup is going to be also IRS. You are kind of trying to follow me because I go from there to there. Okay. So I'm going to use the blackboard. So that's the theorem I'm going to say about free non-abelian free groups, and it's going to be about now that notion about CRS. So every non-abelian free group FR has, okay, so it's uncountably many, it's the same statement as there, uncountably many non-atomic characteristic random subgroups. Now, I don't really need that they are ergodic with respect to the action of the full group of automorphisms, so I'm going to say that they are ergodic under action of FR by conjugation. Okay. So they are ergodic as IRSs, but they carry more invariants. Okay, so I have theorem 2, theorem 1. I'm going to deduce theorem 1 from theorem 2 and then just follow with the proof of theorem 2. Okay, first, so proof of theorem 1 from theorem 2. You take any such group of geometric nature, and there is a general result. It's actually true for any cylindrical hyperbolic groups that it has in itself. So any group, any G from theorem 1, there is a normal subgroup here, which is a free group by itself, which is free. Abelian. Okay. Depending on the type, it's a statement of different people, but I guess in most general case, it was proved by Damani, Girardel, and Osin. Okay, and I'm going to use this result in order to take a random subgroup here and just consider the subgroup in the bigger group. Okay, so theorem 2 gives this uncountably many non-atomic IRSs, uncountably many non-atomic CRSs, random subgroups in N. And so which properties do I have? They are invariant under automorphism group of N, and they're ergodic with respect to the N action. And conjugation. Okay, because it's a subgroup in N and N is a subgroup in G, it's kind of by transition, it's also a subgroup in G. So those random subgroups actually are random subgroups of G. Now the law is invariant under the all automorphism of your group N. And I would like them to be invariant under conjugation by the elements in G. Any element in G conjugates N to itself because it's normal subgroup, and so it induces an automorphism of the group N. So if you have an element in G, conjugating it keeps the law of N invariant because it's invariant under automorphisms of N, in particular under those that come from the conjugation by G. So what else do I need? I actually need that these random subgroups, they are ergodic with respect to the G action, not only, but I already have that they're ergodic with respect to N. Okay? So there are no non-trivial subsets A which are n invariant, and G is bigger than n, so particularly there are no non-trivial subsets which are G invariant, and so I get that since n is just a subset of G, they're also G ergodic. And as I said previously, they are invariant under conjugation by G. So as long as you use this kind of powerful geometric result by the Manij-Radel laws, and you reduce it from those geometric groups to a free group.
So this n comes basically from some sort of small cancellation type considerations with a normal closure or some small cancellation type sets, right? Is that?
Well, I think at least in hyperbolic, yeah, but I don't really know about the other one. So.
Rotating families.
Right, but morally speaking, that's where all of this. Okay, never mind. I think that's where they all come from, right?
I think so.
Okay.
So, but for hyperbolic, what's small conjugation, small cancellation?
Well, I mean, the point is that when you have a small cancellation set and a free group or a hyperbolic group, the normal closure of a small cancellation set is a free normal subgroup. So I think it's true in this hyperbolic or hyperbolic as well. Or and they may not use small cancellation theory as such, but they use some substitute for it.
Okay, so yeah, I'm done with abstract type of groups. I'm going to talk only about free groups from now on. And that's a statement I would like to show.
Those don't have to be finite rank figures are to be.
No, it can be anything. Yeah. Well,
Yeah,
finite or infinite.
Yeah, in fact, this n is.
In fact, you need infinite. Yeah. But I'm going to show it for any. So I'm going to this theorem 2 is I'm going to prove two statements about it. So let's say it's like A and B. So it's proof of proof of theorem 2. Statement A is if n is a characteristic. So it's not probabilistic at all. It's just about characteristic subgroups of a free group. If n is a characteristic, I didn't define characteristic. It just means that it's invariant with respect to automorphism. Yeah? So, and sometimes I say about automorphism. Sometimes I talk about characteristic. That's the same thing. So characteristic subgroup of F. And I would actually like it to lie in a commutator. So we will construct characteristic random subgroup in N that is non-atomic. F ergodic and spans N. And this B statement, which I want to, yeah. There are uncountably many such characteristic subgroups. There are uncountably many characteristic subgroups in this commutator. Okay, so the B statement is just about the characteristic subgroups. The A statement is about just one CRS. Okay, not count with many, but just one.
And spans n means there is no other subgroup of n.
Yeah, okay, yeah. So spans means that you can recover this subgroup n from the random subgroup that you are considering. So there is no smaller subgroup that still contains almost all random subgroups that you want to look at. yeah, here I don't really say whether it's characteristic in a full group or just in this group, because it really is the same. If you have a characteristic subgroup and a characteristic subgroup of that subgroup, then it carries on, because it's not like with normal subgroups, it's transitive, and so I just can talk about B. Okay, so if I show both those statements, that means that I have shown theorem 2. Okay. Why? Because, well, first of all, you take those uncountably many characteristic subgroups in your commutator, and then in each one you construct this random characteristic subgroups, random characteristic subgroup in N. Each of those characteristic subgroups will define N, and therefore if you have a different subgroups here, they give you different random subgroups here. So uncountably many, if you have uncountably many fixed characteristic subgroups, you have uncountably many CRSs. And each one of them is going to be non-atomic and ergodic, and that's what we want in the theorem. Okay? So if you have statement A and statement B, you have the full theorem too. Okay, so let me, I don't really care which one, but I'm going to start with B and explain why there are a lot of subgroups like that.
I mean, theoretically, these measures could have been equivalent to each other, right? But the way you, like your part B or like AB together implies stronger statement that you construct uncountably many non-equivalent.
Oh, yeah, but what do you mean by equivalent? I mean, if
you know, the same null sets.
no, they're different then, because they span.
Yes, that's right. But
yeah.
what I'm saying, yes.
Yes, theoretically they can be, yeah, but I mean, I'm not really sure whether they use as a dynamical system they conjugate, so that's a bit different, yeah.
Yeah, that's different.
But as subgroups, they're different. Okay, so why there are a lot of characteristic subgroups? So it's actually connects to some theorem of Adyan from 70s, and I'm just going to relate it to my statement. Okay, so let I be a set of rods in x1, x2, and all this stuff, and inverses. So for example, I don't know, x1 squared or x1 cube x2 and something like that. You have finite words. Now you take any G and you define a group. You define its subgroup as a subgroup of G generated by evaluations of elements in I on G. So you just take this your word in I and place, instead of letters, you place elements of G and you get a subgroup. For example, if you take I to be x1 squared, then G of I is going to be just a subgroup generated by all squares. It's clear, I should be clear, that any such, for any set like that, this subgroup is a characteristic subgroup of a bigger group. And so that gives me some characteristic subgroups to look at. Now I'm going to say what I want from my set I. So I say that set I is independent if for any word u in I, u is not a consequence of the rest of them. Yeah. So you cannot take words here, multiply them, add them, raise them to the powers, and get u back. Equivalently, and it's easy to show, but I would just say that it's obvious. So that is if you take a free group on infinite number of generators, you generate a subgroup of it by just a single word u, it's not a subset of a subgroup generated by the rest. Okay, now suppose I have an independent set of words.
Sorry, so
Yeah.
just to make sure. So you plug in all possible elements in your group as x1, x2, and so on, and
Yep.
form all possible words like that. Not just that. So there are two options here. You could either enumerate your group and make it correspondence with these indices.
No. Here you have just one index, but a lot of elements. Yeah. Okay, so now if you have an independent set, suppose you have two subsets in it, and they're just different. Okay, then let me look at f infinity a and f infinity b. So they are characteristic subgroups of my infinite group, free group on infinite number of generators. I have a b subset of independent sets. They are different. It means basically from this statement, it means that those subgroups are also different. Okay. So which means that if I have a large enough independent set, I can take all subsets of it and generate subgroups, and they're going to be different subgroups, and they're still going to be characteristic. Well, and that's actually all I need, because Adyan in the 70s proved that there is an infinite independent set. Okay, so maybe I should. Yeah, 70s proved existence of infinite independent set. Okay. If the set is just infinite, then the number of subsets in it is uncountable, and therefore it gives me the uncountable number of characteristic subgroups. So, okay, so that deals with B. Oh, yeah, we're fine, yeah. Yeah, it was a paper of Adyan which followed this paper by Novikov Adyan about Burnside groups, and I'm not sure that it follows from that statement, but it uses the same technique. Okay.
Great for another Armenian.
Okay, so well, I'm done with B, and I only have to show A. So you have a characteristic subgroup of F. It actually sits in the commutator, and I need to construct a random characteristic subgroup there. So construction. Again, I'm going to consider this n square, and then it's the same I did before. So it's generated by all subgroups. Now let's look at n factored by n squared. Okay, because it's a subgroup of commutate, it's going to have and normal. It's going to have infinite rank, and therefore this is going to be a free elementary 2 group, and it's still countable. So this is isomorphic to just the sum of the 2's over. Because every element here, its square is actually 0, and so that's a 2 group. Okay, it's what I can do This is discrete, countable, so its Pentarget loop is going to be compact. Again, I'm not sure. And it's just a set of all homomorphism from n to z2. And this is isomorphic to the product of z2s. Okay, so it's a compact group. Particular, it's there is a Haar measure and it's finite, and I can say that it has weight 1, so it's a probability. So Haar measure n over square head carries probability Haar measure, probability Haar measure. Moreover, Haar measures are unique, and therefore, if you take any automorphism of n, it gives you an automorphism of this group, and it maps Haar measure to Haar measure, and so it must just fix it. So it's which is automorphism invariant, which is out and invariant. Okay. So I already arrived at some object which is invariant under automorphisms, but I need a random subgroup like that. So what are you going to have? You're going to have take a random element here with law, with Haar law, and well, then what is it? It's a homomorphism from n to z2. Okay. In particular, I can take its kernel. Then the kernel of H is a subgroup in n of index 2, and it's going to, well, this is random, so this object is also random, and it's going to be also automorphism invariant. So is a random subgroup of n, and it's which is out and invariant.
So this kernel be also exactly the stabilizer of the element you took?
You mean H? What is it? Okay. Stabilizer under what?
Of n on the dual.
Action on n comes from conjugation. So yeah, maybe I'm not sure. It may be.
You have an action and you have a probability measure. Your action preserves it, and we have a canonical way of just taking the stabilizers, and that's how you get random subgroups, right?
Yes.
Right. So is that what you're doing? Is my question. Is this the canonical way of obtaining? Let's see.
It's very probable. I just didn't check the details here. So
This thing doesn't show you that it's a characteristic random subgroup, right? This canonical construction taking the stabilizer just says it's a random IRS. But you're getting, moreover, that it's characteristic.
Well, if you you have an action of automorphism on this group, and you take a stabilizer. No, wait. Which action do you consider? If you consider the action of a group of automorphisms and you want to take stabilizers in Z, then that's not like that, because that's a subgroup in M. If you consider,
N on
this, if you
take the stabilizers.
Yes, then it may be like that. It's quite probable, but I don't want to say for sure that it's the same thing as I have here. Okay. I just wanted to, one way I wanted to write like that is that it's kind of obvious how do I get it. Because any element of a dual is just a homomorphism, and you can look at some things about that homomorphism, in particular its kernel. And that's what we have. So no, because Haar measure is not concentrated on a unit element, this is not a fixed subgroup, and therefore it spans n because it's just of index 2. So we have that this random subgroup, CRS, this CRS, spans n. What else do I need? Okay. It is also non-atomic. It's easy to check that it's non-atomic. Is non-atomic. And so we only need to check that it's ergodic with respect to f action. Wow, okay, so instead I'm going to say that need to check that the action of f by conjugation on this dual, Van-Tragen dual, is ergodic. Okay. So if this section is ergodic and this random subgroup is just a factor of this section, then we will have that ergodicity is preserved under factors, and so my series is also ergodic. And therefore, I just need to consider this specific action of f by conjugation and check its properties. Okay, so let me erase that one. I reduced this statement A to the following.
So this kernel, okay, you said index 2 subgroup then?
Well, it's still an element from n to z2. If H is not a trivial homomorphism, then it's index 2. Okay, so statement, proposition, f and R is ergodic. Ergodic dynamical system. Okay, now there is a well-known lemma which I probably just state. It's easy to show. So lemma. It is enough to show that the action of f by conjugation on the group itself and 2 has what's called has infinite orbits except the trivial one, except orbit of 0. So it's kind of so it's usually present in all textbooks on ergodic theory. So what do you need to show that this one is ergodic action? You need equivalently, you just need to show that there are no invariant, no functions in L2 which are invariant under f and which are not constant. Because that would mean, you take its level set or whatever, and that means that you get a non-trivial invariant subset here. And so you want to consider L2 of this space, and you want to show that if there is a invariant function, it's constant. And you basically show it by saying that you consider this group. You say that each element here defines an element in L2, and the whole set is, okay, maybe I should. So you define G by E by I, G for G is. So any element here gives you an element in L2, like that. The whole set of those elements will be a basis of L2, orthonormal basis. And then you check how f acts on that orthonormal basis. It carries it to infinity, everything but the trivial one, everything but g is 0. And so it's kind of, it means that any function in O2, f, at least some sequence in f carries it to its integral. Okay. And I don't want to really say anything more about that.
Does it end up being just a shift action somehow on Z2? Not shift, but maybe some, you know.
You mean here?
Yeah.
You see, in order to take that, to get this isomorphism or this isomorphism, you have to choose a basis.
Yeah.
That's not what I'm doing here. I'm just taking
No,
all elements.
Basis,
Yeah.
somewhere else.
And I'm not sure because I mean you can choose the basis in different ways. So how the I mean, you choose it one way, and then your group acts on it not only by permuting that basis, but also, you know, multiplying the elements. So it's not really that it just shifts it. Okay, so I want to say this. That the conjugation of f by, on n factor n square has infinite orbits. I'm done with Pontryagin duos, I'm done with ergodicity, I'm done with everything else. I just need to show this statement. So I'm going to show, I mean, to explain a bit stronger statement. And I'm almost out of time. So let f be generated by, so it's a free group. I choose any free generating set. Let's take any element here. So I was going to say that there is a free generating set D of my group N. Okay, so I'm not going to factor it. I'm just going to look at the group itself. It's a characteristic subgroup here. So this set, it's a free generating set, and it's going to be conjugation invariant under S, not conjugation invariant under S naught, and all S naught orbits in B are infinite. Okay. So I don't care now about the whole F. I just take one element in its generating set, and I say that there is a free generating set in my group N without even factoring it by N2, so that this S naught carries it, you know, in infinite sequences. So it doesn't fix any finite subgroup. Then, because this B will give you a basis of this factor group, it means that if I have that statement, I actually have infinite orbits for my action of F. Actually, just if you restrict this action to the action of S naught group generated by S naught, then it's still true. And the F is bigger one. Okay, so
By saying it has infinite orbits, you don't mean that every orbit is infinite, that some orbits are infinite?
no, I mean every orbit besides the zero orbit. It's a subgroup which is contained in the commutator, so it's kind of, you know, deep down in the group.
Okay, but then the statement will not be enough to prove that every orbit is infinite.
Why?
So, but why will it be enough then?
You take any, okay.
So this is just about a basis, you know, so what's the logic here? You know, what the punchline?
No, that's a basis. It gives you.
On the basis elements I can see it, yes, but on arbitrary elements.
Okay, well, let's look at this group. Yeah, it's just a vector space.
Yes.
That's the basis of that vector space. So you take any non-trivial element here. It just consists of a finite sum of those basis elements. On each one of those basis elements, S naught carries it. It has an infinite. So I mean, it's like a finite number of basis elements here, and S naught carries it into infinity, and so it cannot. Yeah, I'm not sure.
Okay, never mind.
No, I mean, okay, yeah, I'm a bit.
Sounds plausible, but
I can.
An application of A to the first element only gives you already infinite. Whatever happens to the other elements doesn't matter.
So I am already over time, so I
Probably
guess.
just 2 minutes and finish this.
Yeah, I mean, okay, I'm going to see. So I'm going to try. So how do you choose free generating sets of a subgroup in a free group? Okay, so let me say it. So the result you can consider kind of. I'm not sure that I would give it in full, but I'm going to try. So consider a Schreier graph of f by n. So Schreier graph of f by n with generating set S, and it just means that I'm not really sure how many people you know. It just means that you take cosets as points, and edges are going to be labeled by elements of S. Okay. Okay, so you have some kind of graph like that. If now I'm going to construct how to just say how you construct a generating subset, a pre-generated subsets of this n. So you take this graph, you take a spanning tree in this graph, like this is spanning tree. It means that if you add any other edge, it becomes not a tree, so it's not simply connected. And then you take any e which is not in a tree and assign to it the loop that you will obtain. So this is e, and this is the corresponding loop in the graph. But I don't know, it's p of e. This is a loop. Because it's a loop in this graph, it's an element of your group n. So p is going to be n. And if you look at all such edges, you would get a subset of n, and it's going to be a free generating subset. So free generating subset of n. And yeah. Okay, one more minute and then shoot. So you take this n, you add s naught element to it, and you generate the group. It's basically because n is normal, it's just the union of cosets. Okay. You consider graph f factored by g. That's a small graph. F factored by n is a larger graph, and the corresponding projection is a covering map. So this is g of n goes g to g is a covering map. So I have this f of g here. I have f of n here. It's kind of infinite number of copies of that one. The element g is its pre-image, and the pi is, n, and then s naught n, s naught inverse n. So I want to. This is my graph. I want to find the spanning tree here. I'm going to find the spanning tree here, erase it by taking its pre-image. So it's going to be the same tree in all those pieces. This is not a tree because it's disconnected. So it's a forest. You add those vertical edges, which are labeled by s naught. You get a tree, and that's exactly the tree that I want, and I shouldn't go further. So that's the tree that will do the job. OK, that's all. Thanks.